As Tim introduced me earlier, I'm Matt Blood, Director of EdTech Solutions. For my sins, I've now been doing glasshouse heating for around about 21 years now, apart from a short break where I went out and did biomass boilers for one of the UK's leading biomass installers. I'm just going to run through the basics of the different boiler types and the ancillary components, the fuel feed, the storage systems, how we actually connect the boiler to the glasshouse heating system itself. As Tim stressed earlier, every installation is different, so there's no definitive answers. What we really need to do is look at it on a job by job basis. It really is specific to your site. The basic layouts. This is a project that we did up in Carlisle. It's only a little 350 kilowatt boiler, but it does give us the basics on there. What we have here is the fuel store, and in that fuel store we have a rotary agitator, it's a sweep arm, which I'll come back onto those later, but that could be a walk-in floor. It depends on what type of fuel you're using. The basics are the same. Then we have a fuel transfer auger coming from fuel store, which brings it into what is the stoker auger on the boiler. And between these two here, we have this little thing called a drop cell. It's a rotary wheel, which is basically an airlock between the actual stoker auger itself and the fuel transfer auger. So if there's ever a burn back on the stoker auger, it's not coming back into the fuel store. So the theory behind all systems is round about the same. And then obviously we have the biomass boiler itself. There's different types of boilers. We have the underfed hearth boiler. These are for fuels of up to around about 35% moisture content. On these, this is the stoker auger that we just looked at, bringing the fuel into the boiler, and it actually brings it up into the base of the boiler. So the fuel's only burning as it comes into the combustion chamber. So there's no space in there for it to actually dry the fuel as it's bringing in. You're bringing in dry fuel. We then move on to our step grate boilers. This is where we can get above that 35% moisture content. We can put in probably 55% moisture content fuels on these. That's almost straight off the tree when we get to the likes of 55%. And here, what we're now doing, rather than bringing that fuel in the bottom, we're now bringing that fuel into the end of the boiler. We're dropping onto this step grate here. So as the fuel's being pushed in, it's moving down this grate. So as we're coming, the fuel is being dried on this first area here. We have a drying zone. And the fuel possibly doesn't ignite until we're probably about 3/4 of the way down there. And that's so we start burning here. Then by the time we get to the end of the grate here, anything that's left is the ash, and that is dropped off into the end and taken away. The heat is running through the gases are running through the boiler and coming through into a heat exchanger body. The heat exchanger body could either be the top part of the boiler here, or it could actually be a separate unit on the front. There are different types depending on the size of the plant. There's also chain grate boilers, which basically goes back to coal technology, where exactly chain grate. It's a moving grate in the bottom of the boilers. The ones that we've come across, ironically, have been up to 35% moisture content fuels. Again, that is something I have to say I struggle with a little bit, because I do think they should be suitable for wetter fuels. It does give us that sort of step grate principle, but the ones we've come across so far on the market have been up to 35% moisture content. So I think a little bit of a development work there, but there's not an awful lot of boilers on the market that work on that principle at the moment. Most of them are the underfed hearths and the step grates. Physical size of the boilers. Here we have, in the front of the picture, we have a 600 kilowatt boiler. In the back of the picture, we have a megawatt boiler. Well, you can see from the size of these guys here, this kind of scale that we're actually looking at. If you compare that to the likes of an oil or gas boiler, we're talking probably 3 times the size, plus all the ancillaries that go with it, the augers that go with it, the stoker auger, the cyclones, etc. So we can't underestimate how much space we actually need. 3 megawatt boiler. This is one that's actually installed down at Cairnock Plants. Not one of our projects, but it does give a good example. Here we have a very tall Austrian engineer here, so we can see the sheer scale of the boiler at 3 meg. Moving on to 5 meg, this is where we get all the ancillary components added onto the boiler. So just here you can see just by the access platforms around the boiler, flue gas cyclone on here. We are talking about big equipment. We're talking about needing large spaces to actually install this. On this one, just interestingly, where we discussed earlier just about the augers running in, when you sort of get to that 3 megawatt and above, we're then coming on to the realms of hydraulic ram feeds. Rather than augers, we're actually using hydraulic rams, which is what's built onto the front of here. So you've actually got hydraulic rams pushing the fuel into the boiler rather than augering in, just because the augers physically can't put in enough fuel to handle that kind of capacity. 6 megawatt plant. Well, we can see here this guy stood in the combustion chamber of the boiler. So again, the sheer scale of it, you just sort of bring it. We are looking at something an awful lot bigger. We'll get down onto back to the 600 kilowatt boiler. We can get it into probably what is a normal size boiler house. We're talking about a 6 megawatt boiler. You're talking about probably a new build plant room there. Just going back to what I was discussing earlier about the heat exchangers. So generally, what we have is, if I pop us back to that one very briefly, on that 3 megawatt boiler there, we have the combustion chamber at the bottom. We have the heat exchanger body, the boiler tubes, in this top part here. So one on top of the other. Something like that will be delivered to site in 2 halves, put on top, one on the other. That's the alternative. Some manufacturers, what you'll get is your combustion chamber here, and your actual heat exchanger body is actually sat in front of it. Here we're looking at large scale plants. We're talking 3 megawatt and upwards, but again, the actual floor space itself is much bigger on something like that. Boiler selection got to be based on fuel. We're looking at fuel first before we look at boiler choice. Concept of a boiler that burns different fuels is largely a myth. We can possibly swap between the likes of wood chip and wood pellet. You're recommissioning the boiler to do it. If you're looking for something to draw that will burn wood and it'll burn straw, we're into very difficult indeed, without some major changes in between. So it's not a case of doing so many months of one fuel and swapping over. What you're looking at is a constant fuel supply all the way through. Boiler features, the optional extras. What we're often asked is, how much maintenance is this going to take? How many hours a day is it going to take to look after this boiler? There's certain ancillaries on the boilers that are almost must-haves. With those features on the boiler, it makes your maintenance an awful lot easier. So just the basics of these, what I'm going to run through is flue gas cyclones, which take the fly ash out of the flue gas, automatic tube cleaning, automatic de-ashing, and automatic ignition. All of which are fairly hands-on procedures if you've not got them. So really going between the difference of what is daily maintenance to probably weekly maintenance. Your flue gas cyclones, and basically your flue gas is brought in through here, flue gas drops, and it is acting like a cyclone. It's spinning the flue gas. And what that's doing is it's then dropping the fly ash out of the gas and collecting it into a bucket at the bottom. So these are similar to these units here. This is actually a school project where the flue gas is coming through. This is your cyclone body. This is your ash collection bucket on the bottom. We put a 500 kilowatt boiler in at Lenoy's Nurseries down in Cornwall. Now he's collecting half a bucket a day in that. And but what we're actually seeing because of that, when it comes to end of the season, and you're looking at glass cleaning, there's very little, if anything, on the glass house roofs or in the gutters or anything. That is taking out all that fine ash that without that unit on there would probably end up on the likes of your glass house roof or on the neighbour's windows or something like. That's it. Not a vastly costly option, but something certainly worth having on the units. Automatic tube cleaning. Obviously, with it being a solid fuel boiler, as the gases are running through the tubes, the soot's collecting on the inside of the tubes. So again, we need some sort of automatic cleaning system in there. Otherwise, what we're doing is we're opening the front door and we're manually cleaning the tubes out. A couple of different types. Here we have, this is an installation we did up in Wiltshire. It's for a district heating scheme. This is air shock cleaning. This is run off a compressor. So each one of these units on the front is a jet. So they're all timed. So individually they will go off and put a blast of high pressure air through the tubes, blowing the soot into the ash collection boxes at the back of the boiler. Very effective. The only thing I would say on that, it is each one of those going off is almost like a shotgun going off. So depending on where your boiler is located, if you have to live next door to it, like this one, what you have to do is put a timer on it so that it doesn't go off between 9 in the morning and so it's just doing it daytime. It's not going off in the middle of the night. These are timed to go off around about every 5 hours. But then obviously you're not going to do any real issues by not doing it through the night. If you were manually cleaning it, you'd probably only be doing it once a week anyway. Another alternative is some boilers will come with an oversized flue gas fan. So normally your induced draft fan for the boiler that's taking the flue gases through the boiler and up out of the chimney. That fan can be oversized, so it's normally only ever running at half capacity. What it will then periodically do, it will shut this damper off, and that fan will speed up. So we're actually now using the flue gases to blow that back through the boiler and clean those tubes out. Again, it depends on manufacturer. Different manufacturers, different ways of doing it. The effect of not having automatic cleaning on there. Basically, if we very basically look at a year's period and we look at the efficiency of the boiler here, if we're looking at round about 92%, if you don't clean it, what we're going to get is this effect, to the point of where you get to there, or I better clean my boiler, right, I'm running at full efficiency again, and it drops off. What we're achieving by the automatic cleaning is that we're maintaining that efficiency throughout the season. Your automatic de-ashing, that's really where we're taking the ash from the combustion chamber. And again, that is generally, if you've not got it, you're opening the boiler door and you're actually scraping that ash out. Theoretically, that's a boiler shutdown, open the door, scrape it out. If we've got automatic de-ashing in there, we've got another auger that's actually taking that ash out of the combustion chamber and depositing it into something similar to that. Again, different boilers, different makes, different sorts of bins, but that has been automatically augered into there, so we can then wheel it out and empty it out. In effect, what we're left with in here is potash. You can also, depending on how big your boiler is, you can put that on your garden. Just a quick one on the differences here. What we've got is the ash here that's come out of the combustion chamber. Quite a coarse ash. As I said, if it's not quite running efficiently, what you'll be seeing in there is a little bit unburnt fuel. It should be coming out ash, but it's quite a coarse ash. What we have here is the very fine stuff. This is the fly ash. This is the ash that's coming out of the cyclone. Very, very fine. So that's the difference. That's what could potentially end up on glass house roofs and the like if we're not running with something like a cyclone on the back of it. Automatic ignition. Generally, These are heat guns, electric heat guns, and that's just heating the fuel up to a point where it will ignite. Again, if we've not got this, you're actually opening the boiler door, you're putting in the fire lighters, and you're doing a manual light on the boiler. If the boiler's sized correctly, chances are you're probably only doing that at the beginning of the season, and it'll run all the way through, because what we're trying to do is keep that boiler running, because it will go into slumber. As if the boiler does shut down, it will smoulder for a period of time, and then when your demand's back, it will fire up. But if it's left for too long and it does go out, you're back onto a manual relight. So again, it's an option worth having. There are some units where this can be an oil or gas burner that's actually fitted into the unit. And what you can actually, I've seen units on these where they're actually sized to the capacity of the boiler, or so you lose efficiency in doing it, but the size to the capacity of the boiler. So you're actually putting yourself a backup burner in there. So if there is a fuel issue, you can actually run that boiler on oil or gas. Not a cheap option, but it is there as backup if you need it. Let's quickly touch on ceramic filters. There's a possible scenario within the renewable heat incentive that could focus on emissions. So I can see again, we've got to counteract this. What we're hearing is that it's probably largely focused on NOx emissions. So what we're looking at here, flue gas cyclones, they're not doing an awful lot for NOx, but we are taking out the fine particles. Exhaust gas recirculation, that's where they actually use exhaust gas, bring exhaust gas back through the combustion chamber to actually control the combustion temperature. And in doing that actually lowers your NOx emissions. But we'd like to think that is going to be sufficient to meet the NOx regulations of RHI if that's what's coming. If they don't, what we've got to look at are filtration units. A possible example of that is ceramic filter units, where we have ceramic tubes in housing behind the boiler. There is a cost to that, but until the RHI is known, it's a difficult one to predict. But I think at the moment, when we're looking at costs, we've kind of got to allow a sum of money to cover that. Fuel storage options. That's what we're trying to achieve. Is when you get your wood chip delivered to site, ideally we want to be tipping straight into your fuel store. To build a hole in the ground, that can prove quite expensive. If your site's got a natural slope to it, you can possibly utilise that. Look at utilising a natural slope in there, or we'll possibly look at building some sort of ramp up to a fuel store, so you can deliver into it. It may well be on the quantities that we're looking at, you're actually delivering your wood chip into a separate store anyway. You're just delivering it onto a barn floor. So possibly using a front loading bucket to bring it to your main fuel store. So it's not really an issue if we're looking at those kind of quantities. Smaller boilers, if we're looking at boilers of probably up to 500 kilowatts, we can look at rotary agitators. So here we have a square bunker with a sweep arm in there. That arm sweeps around, and we're bringing the fuel into this auger here, which is then passing into the boiler. Roundabout in those stores, you'll get roundabout 50 cubic meters of wood chip. 50 cubic meters of wood chip, 37,500 kilowatt hours, there or thereabout, depends on moisture content. So on your 500 kilowatt boiler, that'll give you 75 hours, around about 3 days at full load capacity. That boiler will running flat out. So really, what we're doing, what I'm trying to get to there is that kind of fuel store, you're really reaching your limit at around about 500 kilowatts, 600 kilowatts possibly, but that is kind of your limit. After that, we're really looking towards walk-in floors. Walk-in floors are basically a metal grate on the floor, controlled by hydraulic ram. So these grates will actually slide. These grates are pulling the fuel up the fuel store into what is an auger that runs across the back of the store. Now we can line these up side by side. We've these grates can go 10, 11 metres long, probably at a maximum. What we can do is you can repeat that side by side, one on another, and what you can do with then is you're delivering onto a flat floor. So that's realistically what we're probably looking at. You're looking at a barn with the walking floor built into the floor where the wood chip is piled on top. What we've got to consider, it's got to be high enough. Because if you're coming in with large tippers, you need the height in there to be able to get it tipped on. Some of these walking floors you can't drive on. Some of them you can. Some of them, if you've got 4 inches of wood chip on top of the walking floor, you'll be able to drive a front loading bucket on there. Again, there's different units on the market. Different manufacturers will offer different systems. So we should be a little bit careful about what these walking floors will actually handle. Straw burning, another possibility. What we're looking at here is conveyors. These conveyors are generally long enough to take a day's worth of bales. And the bales are running down here into a chopper unit at the end. Again, another option. I'm not going to go into the technicalities of it, but it is another option there based on your fuel choice. Yeah, straw burning. Again, what we've got this conveyor here running up. Here we've actually got an overhead crane unit taking the bales in and into what that one is actually. That's like chopping the bales rather than shredding bales. That's chopping bales to then take the straw into the boiler with a hydraulic ram feed. But again, what we've got to look at is this vast area that you do need for fuel storage. A few issues with straw burning. High sulfur contents, high chlorine contents. In the early days, rule of thumb was your straw burning boiler will last 25 to 30% shorter time than your wood chip boiler would. These days, they're starting to change the materials in these now. They are very comparable to the likes of a biomass boiler now, a wood chip or wood pellet boiler.
I guess we haven't got any actual. It's so new. There aren't any boilers that have got that sort of year on the box. So
there isn't. If we're looking at straw boilers, last week we looked at one there, and the boiler is probably 4 years old. And that's probably one of the older straw burning units in the UK.
I think that there is quite a bit of experience in incineration of waste to say that those steels do last. They burn some pretty noxious substances. So there is quite a history about that. So I don't think there's any issue about the new steel in the budget.
No. Okay. Heat storage. Tim touched on this earlier. Your heat storage, it's a similar principle to your CO2 heat storage. Difference being is that we're running these tanks with two flows, two returns on them, which I'll come back onto shortly. What we're looking at, we're trying to keep these temperatures above 60 degrees. Again, I'll come back onto that again shortly. So realistically, what we're looking at is using 25 to 30 degrees out of that tank. So we're not dropping vast quantities, not like CO2 heat storage, but we can link this in with your storage. The nice nurseries, again, so this was a 500 kilowatt boiler. In that one, we put in a 60,000 litre heat storage vessel, so 120 watts. Litres per kilowatt in there. That's quite a vast storage for a boiler of that size, but the theory is it does work. That boiler, basically he fires that at the beginning of the season, and that will run flat out all the way through till the end of the season. Connecting your biomass boiler to your glasshouse heating system. This has been the downfall of a lot of systems so far. I think when biomass started coming into the glasshouse industry, there was a little bit of bad publicity around about systems not working. This is why. This is because they're not connected to the heating systems properly. What we're looking at very basically is we have a biomass boiler and we have our heat storage tank. A lot of biomass boilers early on were connected in as you would do with an oil or gas boiler. On those boilers, pipes up, you've got a variable flow rate through those. The water will you've got variable speed pumps. You've got mixing valves on there. That will vary your flow rate through there. Biomass boilers don't like that because it's solid fuel. It's solid fuel combustion. It wants a constant flow rate. It can't react as quickly to fluctuations. So what we're trying to achieve here, to get the best out of it, we want to keep a constant flow. So what we're actually doing here is we're forming a loop. We're running into the heat storage tank, back out, and keeping this loop here. We're almost trying to keep that separate from your glasshouse heating system. So whether you've got heat demand on the nursery or not, that boiler can run. That boiler is storing heat in that tank. What we can then do is your glasshouse heating system will then pull from that tank as and when it needs to. So if you're not running CO2, if you've not got CO2 buffer, we're sizing that tank to the full capacity of whatever your heat storage is. If you've got a CO2 buffer already, all we're actually doing here is we're trying to make that just an intermediate vessel, because I'm trying to control this no lower than 60 degrees. Why am I trying to control it at 60? Because when I bring water back to the biomass boiler colder than 60, I'm reaching dew point at the back of my boiler. So I'm creating condensation in the back of my boiler. Obviously with a solid fuel boiler, we've got the soot in there. We've got the from the combustion. So that mixed with condensation, we end up with a thick tarry substance in the back of the boiler that eventually will just choke the boiler. So we're trying to keep the back end temperature of the boiler up, which is controlled through this mixing valve here. So ideally, we're trying to keep that tank above 60. But where you have your CO2 buffer, what we're actually doing is treating that as another boiler. You're taking from that tank and filling what will be a separate tank on that system.